Hi everybody, let's talk about percent composition. Now again, you'll definitely want to have a periodic table out whenever we go through these practice problems, and let's start with a little story. So imagine that you are working one day in an industrial laboratory and your supervisor comes up to you and gives you a bottle with a white crystalline compound and asks you to figure out what it is. So here we have you. We have your boss. Neither one of you is following proper safety protocols with your hair tied back and wearing goggles and aprons, but that's okay for this example. So you two walk over to this container and boss wants to know what is in there. And so what do? You need to analyze this thing. And it turns out that there's a warehouse nearby where there are several large containers being stored. And we need to get rid of it somehow, but we need to know whether it's dangerous or not. And so what do? You do an element analysis and you figure out that within this container, within this substance, there is a compound that contains sodium, contains Na. It contains carbon, and it contains oxygen. And so you think of the most common compound you can think of with those three elements, and it's some polyatomic ions that you know, and you think of sodium carbonate, Na2CO3. Maybe that's it. And it's a really common substance. It's found in a lot of laboratories. It's used in a bunch of different industrial processes. But before you're going to report this to your boss, you decide to check out a reference book to see if there are any other compounds that contain only those three elements. And you discover that there's another one, and that other compound is called sodium oxalate, which is Na2C2O4. And you read more about sodium oxalate and you find that it is really poisonous and it can cause serious illness and even death. So if we mistaked our sodium carbonate for sodium oxalate, that would be pretty darn serious. What can we do to identify which one it is? Is it the common industrial compound, Na2CO3, or is it the poisonous sodium oxalate? So we have another method, fortunately, which is that we can, in addition to determining which elements are there, we can figure out how much of each one is present. And it turns out that every element and every compound, I should say, has a very specific composition that makes it up. And so that's what we're going to figure out today. And we can figure out basically how much of these compounds is made up of sodium, how much is made up of carbon, how much is made up of oxygen by mass. So we're actually going to see these two compounds reemerge on your note guide as our first two practice problems. And again, we are going to need molar masses to do this. And as a reminder, on your periodic table, you can find molar masses for elements by looking right beneath the element. So for iron, for instance, it has a mass of 55.845 as its molar mass, which also happens to be the mass of 1 mole of that iron. And so if we wanted to make a compound out of iron, we could add together the iron with whatever elements are in there to figure out the total molar mass. So let's do that for sodium carbonate. We know in sodium carbonate, we definitely have some sodium. And there are two sodiums. Let's do it this way. We have sodium. There are two of these. That means each sodium comes in at 22.99. If you do 22.99, you will get 45.98 as a mass coming directly from sodium. There's also carbon. We have one carbon weighing in at 12.01. 1 times 12.01 is simply 12.01. And we have 3 oxygens. Each one of those weighs in at 16.00 grams per mole. So that gives us 48 once we multiply times our 3 oxygens. Excuse me, 48.00. We can then add those together and we'll get a total mass of 105.99 grams per mole. And so in percent composition, what we want to do is figure out what percentage of that mass is sodium, what percentage of that mass is carbon, and what percentage of that mass is oxygen. So we're going to do 3 different things here. We'll use 3 different colors. We are first going to talk about sodium. And for sodium, we know that we have, coming from sodium, a mass of 45.98 grams per mole over the total, which is 105. 0.99. And if you do that, your calculator will spit out the number 0.4338, which we know turns into 43.38% when we multiply times 100. And if we do it for carbon, we will take the mass 12.01 and divide that by our total, 105.99. And when we do that math, we will end up with 11.33, but it'll actually come into our calculator as 0.1133, which then becomes 11.33%. And then we're going to do the exact same thing for our oxygen. So oxygen has a mass of 48. For oxygen, we have a mass of 48.00 over our total mass of 105.99. And when we do that math, we will get 0.4529, which becomes 45.29%. So at the end of the day, we've looked at all of these different elements. I should have written carbon down here as well, so this blue one is carbon. And those different elements contribute to the overall mass of this sodium carbonate, right? And as they contribute to the overall mass of the sodium carbonate, we can take the mass of each individual piece, and then we can divide by the total. And when we do that, we get the percentage of each individual element. So there's sodium carbonate. Let's do the exact same thing for sodium oxalate. And once we do it for sodium oxalate, then we can, use this data to figure out what we need to tell our boss. So let's figure out the mass of sodium oxalate. We know that we have sodium in sodium oxalate. So we have 2 sodiums. Each one weighs in at 22.99. Multiply those together, you will get 45.98. There are 2 carbons. Each one weighs in at 12.01. So that's 24.02. And there are 4 oxygens. Each one weighs in at 16 grams per mole apiece. So that's 64.00 grams per mole coming from oxygen. That gives you a grand total of 134.00 grams per mole for the total. So let's go through and let's talk about each individual part. For the sodium, we said it has a mass of 45.98 over the grand total, which was 134.00. In your calculator, you'll get 0.3431, which turns into 34.31% sodium. We can also do this for carbon. So carbon weighed in at 24.02 grams per mole over the grand total, which was 134.00. Do that math in your calculator, you'll get 0.1793, which turns into 17.93%. And finally, for oxygen, we said had a mass of 64 over the grand total of 134. That will equal 0.4776 or 47.76% oxygen from this compound. And if you haven't picked up on this already, if you add together these percentages at the end of the day, so if we add up these 3 percentages for sodium carbonate, we will get 100%. And these 3 percentages for sodium oxalate, we should get 100%. So that's a really good way to check your work to make sure everything is present and accounted for. Now, what if we wanted to take things a step further? What if we wanted the percent of water in this compound, sodium carbonate decahydrate? Well, there's good news for us, which is that we've already done a little bit of this work already. So we've already done sodium carbonate, right? We said up here, we said that sodium carbonate has a mass of 105.99. So you can recalculate out the math for this Na2CO3. But because we already did that, we can just plug that in here. So sodium carbonate, Na2CO3, we have one of those. It weighs in at 105.99. So we're going to have a mass of 105.99 coming from our sodium carbonate. We then have water, and water is H2O, right? So H2O has a mass of 2 hydrogens. Each hydrogen is 1.01, so 2 times 1.01 is 2.02. And there is 1 oxygen weighing in at 16. So the mass of an individual water ends up being 18.02 grams per mole. And you'll notice that we have 10 of those water molecules. So we need 10 times this number. We have 180.02 coming from water. So if you add that together, the total compound here weighs 286.01 grams per mole. And it turns out that we are interested in the percentage of water coming from this compound, right? What is the percentage of water coming out of that compound? Excuse me, it's not 180.20, it's 180 point, not 0.02, it's 180.20. So that means that our math here should be 286.19, pardon me. So the total mass is 286.19. We want to know how much is water. So we're going to take the mass of our water, which is 180.20. We're going to put it over our total mass, which is 286.19. When we do that, we will get 0.6297, which turns into 62.97% when you multiply it by 100. And then finally, we can take this a step further. What if we know the mass of our sample, right? What if we have this sample of magnesium hydroxide? So magnesium hydroxide is MgOH2. And we know that we have 175 grams of it. And what if we want to know how many of the grams, of the total grams, are made up of oxygen? Well, another way of asking that is what percentage of that sample is oxygen? So let's do what we've been doing, right? Let's find the mass of magnesium. So the mass of magnesium, if you look on your periodic table, you have 1 of those magnesiums, and the mass of magnesium is 24.31. So 1 times 24.31 is 24.31. There are 2 oxygens. Each one weighs in at 16.00, so that's 32.00. There are 2 hydrogens. Each one weighs in at 1.01, so that's 2.02. And if you add all of that together, you should get 58.33 grams per mole. And we want to know ultimately about the oxygen. So let's figure out what percentage of this mass comes from oxygen. So for oxygen, there's a mass of 32.00 over the total, which we just said was 58.33. And that turns out to be 0.5486. So for 0.5486, what we're saying is that of that compound, of the MgOH2, this compound is made up of 54% oxygen. And so if it's 54% oxygen, let's multiply that times the 175 grams, right? So that number comes in here, of our sample, and 54% of 175 grams turns out to be 96.0 grams coming from the oxygen in this sample. Because if the sample weighs 175 grams and 55% of it is oxygen, then 55% of that 175 is the oxygen. You'll notice that 175 has 3 sig figs, and you'll notice that we finished off with 3 sig figs at 96.0.